In this talk, as you can see, there is the word stochastic between parentheses. So actually, many of these works, including maybe the most fundamental one, they are about stochastic PDEs. But with the limited time, the talk will be almost entirely deterministic. And the key word in this talk is the small-scale behavior. And finally, there is one important thing. Part of this talk is a teaser, because there is an almost finished work with Piotr Biller and Grzegorz Karch in Wrocław and Philippe Laurenceau in Toulouse, which is an extension of what I will present in most of the work about Burger's type system, to aggregation-diffusion, or if you want, generalized Keller-Segel type models. So first I will talk about the behavior of the solutions in the inviscid limit. So in other words, how the models, what kind of explosions or shocks we have. Then there will be the main part which is about the one-dimensional Burger's equation. Then there will be a modification, a good small model modification about the fractional Burger's equation. Then, depending on the time, I will spend I will give a more or less large role either to the random forcing or to the multidimensional situation or to both. So first, I had small-scale behavior in the title of my talk. What do we mean exactly? So first, in the physical space, the meaning is almost obvious. So something which happens on small scale is when you introduce a small space parameter. And bidimensional reasons in Fourier space, for instance, if you consider a spatially periodic model, the scale can only be the inverse of the Fourier frequency, which we are studying, where something interesting happens. So it's the two canonical small-scale quantities for a function which is defined in a periodic setting. It's the Fourier coefficient u hat of k for large values of k, or the increment u of x plus r minus u of x for small values of the separation r. And the one important thing, in order to avoid the future confusion, in this talk, when we mention scales, it's only space scales. Just the time scales are, of course, very interesting, and there are results about this type of model and their behavior in long time, but, well, the time doesn't permit us to talk about them. So now, what type of results do we expect and do we prove? So the general logic behind the things I'm presenting is to study the behavior of PDEs which come from different sources. Well, my model example is the different Burger's type equations are originally from hydrodynamics. The aggregation-diffusion equations are originally from biology, as Ariane reminded us in the previous talk, for the Keller-Segel type models. And actually, both of them are also linked to astrophysics. And the key idea is to look at them when the only parameter which varies is nu, which I will call the viscosity in this whole talk, and all the rest stays the same. So now let me talk to you about a motivational example, which is of course far, far too complex. It's the 3D Navier-Stokes, where you can, it's the usual uncompressible 3D Navier-Stokes, where you put some viscosity, and the question would be, what happens at small scales? Okay, this example is of course much, much too hard. There are very well-known analytical problems with Navier-Stokes. It's one of the 3D Navier-Stokes is one of the clay millennium problems. And when in texts about, like the book of Uriel Frisch, about foundations of fluid mechanics and of their mathematical study and of turbulence, there is an evocation of that it is a very old problem to see what happens on small scale for a velocity field of turbulent fluid. So let me give you a very naive example. So what do I mean by small scales? And actually, let me be more specific. It's moderately small scale, and I will explain right now what I mean. So the naive example is that we have a cubic tank which is filled by water. So then you do something with this cubic tank. Well, you have water which has to, for instance, you consider it with some type of forcing, and you need to have water which comes in and which goes out. And you want to prove something which is at once interesting and a little bit universal. So I mean, which does not depend, which only depends in a simple, straightforward way of the particular features of the model. So on scales which are large, obviously everything depends on the particularities of the model. So what kind of forcing do we have? What are the shape and the position and the size of the holes? So on large scales, clearly, no hope of anything universal. And on scales which are too small, okay, so Kolmogorov never, well, at least in these papers, Kolmogorov never specifically spoke about Navier-Stokes. However, the general idea is still the same, which is that at scales which are too small, you have a damping, and which basically doesn't allow us to see anything interesting. So, as I said, the large scales can't be universal, and on small scales, everything is damped out. So the only place, on the scale level, the only place where you can observe something interesting are moderately small scales, well, in some specific sense. So again, it's a very old problem. It was considered by the classics of fluid dynamics beginning from the 30s, so Taylor and Don Zager. But arguably the three most influential papers on the subject, it's Kolmogorov in 1941. So in the future, I will refer to some results of this type as the K41 theory. So now let us get a little bit back from Kolmogorov and into PDEs. So the small-scale quantities are mentioned, which are the increments in the spectrum. There is a relation with the two-sided estimates to the Sobolev norms. So for the spectrum, there is something very easy to see for the HM Sobolev norms. So the HM, I remind, it's okay. The HM semi-norms are the L2 norms of the mth derivative in space. So they are just defined through the spectrum. So the link between the spectrum and this type of functional norms is clear. And then for the increments, it's a bit more indirect to relate them to Sobolev norms. And you have to remind that, I remind that there are different kinds of functional norms, which just in the definition, there are increments. And then, so you can define these norms through increments, and then you can inject them into Sobolev spaces. So there are two-sided relations which allow us to connect results on Sobolev norms to results on small-scale behavior. So in the PDE literature, there are many results for Sobolev norms when you have a small parameter, so 2D Navier-Stokes, and then many other type of equations, so many dispersive models like nonlinear Schrödinger, Korteweg-de Vries. And there is just one important remark: there are results which are both with and without random forcing. And actually, for many systems which are, well, in a very loose way integrable, results with random forcing are somehow nicer than results without random forcing. Because without random forcing, you can get stuck in pathological regions, and the forcing allows you to get out of them. Well, it's somehow, it helps you to regain some kind of genericity. So yeah, okay. There were two papers by Cookson 20 years ago when the theory is still a bit in its infancy. And more specifically on the subject of the 2D Navier-Stokes, and this is a much easier to read and more structured. There was a book of Cookson and Chirikian from 2012. And for these equations, the estimates are not sharp when the viscosity coefficient goes to 0. What it means is that okay, it's already quite an achievement to have lower and upper estimates for Sobolev norms, but typically you have powers of the viscosity coefficient nu, negative powers, which are different from lower and upper estimates. So, well, there is still something which needs to be understood on these models. Somehow the sharp behavior is not 100% understood. So now, let me tell you that, as you can maybe guess, in the models which will be presented in this talk, the results will be sharp. But before we consider results for small nu, which are asymptotically sharp in the limit when nu goes to 0, let me tell you what happens when nu is equal to 0. So before studying the 1D Burgers equation, let me tell you about a very classical estimate. So I call it Oleinik's estimate, but it's something which was proved in the 50s, and it's, well, Lux and Hopf also have similar results in their papers, if I'm not mistaken. Let me explain what happens on a very simple toy example. Sometimes the Oleinik estimate is referred to as a maximum principle. I am not a big fan of this denomination because somehow the maximum principle makes it feel too PDE, but here it's more just elementary analysis than PDE. It's only Taylor's formula, I want to say. So we want to look at this equation, and we want to obtain bounds from above for the spatial derivative, and we want this bounds from above not to depend on the viscosity. Because of course, if you're allowed to take into account the viscosity, then we have a usual parabolic equation, and we have some estimates which depend heavily on the viscosity. So how do we do it? We consider the function v, which is t times ux, so on this domain. On this domain is space-time, so it's a cylinder, because we're in the periodic setting on the circle, so there is no spatial boundary. It's a cylinder in space-time. So this function obviously vanishes when t equals 0. So if you want it to reach a positive maximum, it has to be for t strictly larger than 0. And then let's just apply the Taylor's formula at the point where this maximum is reached. Okay, you want to say that this term is 0. It's almost always the case, except if the maximum is reached at the top of the cylinder, so when t equals big T. But we don't care, we just need it to be larger than 0. Okay, so since there is no boundary in space, this term has to be 0. And finally, the second derivative at a maximum is negative. And we don't care about the viscosity. This term has a good sign, we're happy. We don't care whether the viscosity is 10 to the power 7 or 10 to the power minus 7. And because of all of the three things I wrote, and again, the proof is very elementary, the term v has to be smaller than 1 in order for the thing in red to be negative. And so we have something which is very strong. We have this damping for the positive part of the derivative. So I like to refer to it to inviscid damping because, as I said, the strength of the viscosity plays no role. But one thing which is very remarkable is that not only the damping is inviscid, but it's totally independent on the initial condition. You can put whatever you want. It will still be bounded from above by t to the power minus 1. Just one last thing to say about it. It's very robust. You can put in an additive force. Well, if you put in an additive force, of course, this thing will be totally false in long time. But in short time, you still have this damping as t to the power minus 1. So now, why this damping is one of the reasons why this damping is of interest for us is because this results pass to the inviscid limit, so to the entropy solutions. Because in this case, it is if you refer to the lecture by Alexis Vasseur this morning, this is the perfectly nice case where because you have a strictly convex flux. So the inviscid limit is unique and well defined, as it's just a usual limit in L1. And for the solutions of the inviscid equation, the Oleinik estimate passes to the limit when nu goes to 0. And then, in this case, okay, we need to be a little careful about the space average. Actually, it works in all cases, but let's just put the spatial average equal to 0, which we will do until the end of this talk. And if the spatial average is equal to 0, then the L2 norm is just bounded from above by the max of ux. So the energy of the system, which is the square of the L2 norm, will be bounded from above by t to the power minus 2. So you have dissipation. On the other hand, if you just consider the equation formally, assuming the solutions are smooth, then you see no dissipation, because the term which corresponds to the nonlinearity, if you integrate over the circle, it vanishes. So we have a contradiction, and the only way to solve this contradiction is if the nonlinearity does not vanish, which is only possible if the solution is not smooth. So it's a very elementary way to show existence of shocks. There are many other ways. Of course, the canonical way is through characteristics, but actually this method is more flexible. I will show it later in a more general setting with a fractional Laplacian. So it's an energy method plus Soleinik. So for the multidimensional Burger's equation, there is an analogous issue, but it's a bit more delicate because actually the nonlinearity does not vanish. So you need to add some forcing, some random forcing, or you need to add some assumptions on the initial condition. And now about the teaser I mentioned in the introduction, for the Keller-Segel type models that we are now studying, it's also a very, very elementary argument why you even have something worse than shocks. You have blow up, just differentiating the energy. You have a very simple argument why you have blow up for our models, just comparing to the solution of an ODE. So before talking more specifically about the details of 1D Burgers, let me tell you one thing. I'm talking about systems which blow up when you have no viscosity, and which by the usual parabolic theory, you know that everything is totally smooth when nu is larger than 0. However, something needs to survive from the blow up which happens when nu equals 0. And again, I would like to insist, this is what my whole talk is about. So here's the periodic generalized Burger's equation. Okay, so the generalized is not extremely important. Well, F has to be strongly convex though, because it is by far the nicest setting. And I just want to insist on the fact that F can be more general than u squared divided by 2, because actually when it's u squared divided by 2, then there are some integrable properties. You can map this equation to the heat equation through Hopf-Cole. I would just like to emphasize I do none of it. Like my estimates never really use this particular nature of the quadratic term. So just a small historical physical background. As you can see, this in the case f of u equals u squared divided by 2, this is exactly, well, okay, it's an equation which is a little stupid because it's incompressible Navier-Stokes without the pressure. So for this reason, it has been considered by many physicists, including physicists which are interested in stuff pretty removed from turbulence, like Polyakov. And also one case where it's also considered in the inviscid limit, and in the multidimensional case, it's Zeldovich who studied it to model the large-scale behavior of galaxies in astrophysics in 1989. Okay. Maybe I have repeated it too much, but here the only parameter which changes is nu, so the viscosity coefficient, which is small and strictly positive. And one last remark, so it's not conceptually deep, but to make our notation much simpler, we always assume that at each given time the space average equals 0. Just, well, essentially this ensures that Sobolev norms and Sobolev semi-norms are equivalent. And it's, okay, I'm making it seem more complicated than it is. Actually, it's enough to assume that the initial condition has space average 0, and then it's easy to see that this property remains true for all times. So here's the typical profile of a solution after time of order 1. You have an amplitude which is also of order 1, which follows from the Oleinik estimate. And what survives from the shocks are the cliffs here. So because of the convexity assumption on the nonlinearity, you only have you have jumps which go down, and the typical size of a jump is of order 1. If we waited long enough for the singularity, if we waited long enough, then in the inviscid case you have shocks, and in the viscous case you have these negative jumps. And I have one last heuristic statement, which was already there in the physical literature and which we'll make rigorous, which is that the typical width of of this viscous layer or cliff is of order nu. So it's okay. There is a good physical review article by Beck and Hanin, where they use the term turbulence. I don't want to comment too much on it because nobody can agree about what the definition of turbulence is anyhow. However, let me tell you something which is more clearly true. That is that we have a ramp cliff structure with nice smooth ramps and sharp cliffs. So we clearly have intermittency, which we can quantify. So it's a good example of intermittent behavior. Now I will state the results. So let me introduce the notation. This notation just means that the quantities x and y are the same up to a multiplicative constant, and this constant is only allowed to depend on the parameters above the tilde. And I would like to insist that I will really track in a sharp way the dependency of nu. So if something depends on the viscosity coefficient, I will tell it explicitly. This is just the usual Lebesgue norm in LP. So, okay, on the circle, it will become on the torus later in the multidimensional case. This is the Sobolev norm in the space WMP, and since we have zero space average, it is equivalent to consider the Sobolev norm and the corresponding semi-norm. So the norm in the Lebesgue space LP of the nth derivative in space. This is the Sobolev norm in fractional Sobolev spaces built over L2. So in the case when alpha is integer, it's just a particular case of this. In the case when alpha is not integer, it's, you define it through a Fourier multiplier in the torus. I can recall the definition later, but well, sometimes the fractional appellation can be very tricky on domains. On the torus, there are no such problems. There are no boundaries. It's a very straightforward, it's just a very straightforward Fourier multiplier. And okay, so all this notation was relatively standard. The only thing which is not standard are the brackets here. And you need to be careful because in the next sections, I will change the meaning of these brackets. So what they mean is that we take some average over a time period. And this time period, it depends on the initial condition, and we have no choice. Why do we have no choice? Because we have a system which is purely dissipative. We have some energy in the system in the beginning, and then we have nothing pumps energy into the system. It is only dissipated through the viscous term. So in other words, if we want to describe some interesting transitory behavior, the interval in which it is observed has to depend on the initial condition. And actually, it's very straightforward. It only depends on the, well, on the L infinity norm of the solution and its derivative. And actually, the dependency is very straightforward. It's a product of powers of these terms. So here are the estimates. Before, there is something I really don't want to forget, which is that Biryuk, who did his PhD thesis also with Cookson before me, had the first ideas for this, but his results don't cover the whole range of the norms, but he had some key technical ideas which are used in my proofs. So let me state what the result is. So you take almost any Sobolev norms you want, just p equal 1 is forbidden, and you take any moment of this norm you want. So for any b larger than 0, and you take the average in time over the interesting time period. And then you can estimate all these objects as negative powers of the viscosity coefficient nu. So let me make some comments and about why, sorry, gamma. I forgot to talk about gamma. Gamma is the number of derivatives you need to take minus 1 over p. So for those familiar with the Gallardo-Nirenberg inequalities, it's exactly the same thing which you find there. So somehow it measures, morally speaking, it's a more refined way of measuring spatial regularity. So why am I saying that it's sharp? First, okay, the first way in which it's sharp is very straightforward. It's encoded by the tilde here. It's just that the upper and lower estimates are the same up to a constant which only depends on the viscosity. Which does not depend on the viscosity, of course. And then the second thing, which is a bit more subtle, you need to look at what the power beta does. And what we see is that the average in time of the power beta of a norm, always up to a multiplicative constant, is the same thing as the power beta of the average in time. So depending on whether beta is larger or smaller than 1, we saturate Hölder's inequality one way or another. And actually just by Chebyshev's inequality, there is nothing tricky here. There is a very important consequence of this fact, which is that the times when the Sobolev norm behaves like its average, the measure of these times is of order 1. So what I mean is that not only we have estimates for averages, but actually on a large enough set, we really know that the norms behave exactly as is written here.
In this bound, the T1 should be large enough depending on the initial data.
Yes.
T2 can be quite arbitrary.
T2 can be quite arbitrary. Well, the constant gets worse, Mauro. The constant gets worse because it's you dissipate, and your solution becomes smaller and smaller.
I mean, that's the scaling of the single shock, right?
What do you mean exactly?
I mean, if I take a solution which displays a single shock,
yes,
I would get the scale.
Yes, it works. Well, you will see later in the proof. An important part is that at least one shock did have the time to happen. That's the key. At least one shock did have the time to happen. That's the key statement. So now let me give some ideas of the proofs. For the upper estimates, the Oleinik's estimate, which I already presented, of course, plays a key role. And then to propagate to higher Sobolev norms, it's the energy estimates in the sense that you differentiate what we can call higher order energies. So just you differentiate this term, and then you have some interplay between what's due to the nonlinearity and the viscous dissipation. And you need to use the Galliardo-Nirenberg inequality in a smart, sharp way. So for the exact lower estimates, so let me tell you how it works. And again, the energy balance, which I briefly mentioned before, plays a key role. So as I mentioned before, the contribution of when you differentiate, so it's the H0, which is just the L2 norm. When you differentiate it, the contribution of the nonlinearity disappears, so you're left with this. And on the other hand, by Oleinik's estimate, the energy has to decrease like at least like t to the power minus 2. So if you have some initial condition, and then you decrease, which means that the time integral of the dissipation has to be of order 1. And which finally means that the H1 norm squared has to be of order nu to the power minus 1. So this is what gives us our first lower estimate. And then you use the Galliardo-Nirenberg inequalities. If you have one good upper estimate, if you have many, not necessarily, no, actually one lower estimate is enough, one lower and one upper estimate is enough to use Galliardo-Nirenberg, and for the lower estimates to propagate up the scale to higher order spatial derivatives. So here I give a little more details about how we obtain the lower bounds. You integrate in time, and then this guy decreases again like t to the power minus 2. Then you have to wait long enough depending on the L2 norm of your initial condition, and you obtain this estimate. So the square of the H1 norm, if you average it, it's larger than a constant time nu minus 1. Okay, now we forget absolutely everything about the equation. We just have Oleinik's estimate. We have the estimates about time averages of Sobolev norms, which I just mentioned. And now we use them as a black box. to obtain results on the small-scale quantities which are traditionally of interest to people in the fluid dynamics community. So this object is called the structure function, but it's just it's the moment of increments. So you take the same time averages as before. You have no choice. And then you also need to average in space. And on the Fourier level, you average, okay, you take the energy which corresponds to n to Fourier modes of order k, and then since all our estimates are true up to a multiplicative constant, we need to average over a layer of n which are of the same order as this quantity k. So and now we have something which is a little strange when you see it first, which is that we had our previous results which depend on the viscosity, and we obtain results on small scales where you see no viscosity at all, which are uniform with respect to nu. So which say that these quantities do not depend on the viscosity, the SP, so the average moments of increments, and the same is true for the energy spectrum. But actually, if you look more carefully at the formulation, the dependence on the viscosity is here. And I will make a comment. If you remember this cubic tank which I drew before, where I say that the only scales for which you can obtain results which are interesting and universal are the scales which are small and not too small. And this is exactly what happens here. So you have some upper bound, okay, which only depends on the initial condition, because here we have nothing else in the model. This is what this constant depends on. And then we have a lower bound which depends on the viscosity actually. So here we quantify in a very sharp way what do we mean by scales which are small but not too small. And in this region we obtain something universal. So, okay, I have the 20 minutes left or more? Okay, good. So I have the time to make a few comments on the proof. So how do you derive this from the Sobolev norms? So for the lower estimate, as you said, it is the scaling of a shock. So it's, okay, viscous shock is a bad term, it's viscous layer. So the lower estimate, it's obtained by using the fact that in the inviscid case, you have at least one shock which had the time to fully form, so to be of size 1. So actually, here we really use the structure of the viscous layer. Let me come back a little bit. You see this viscous layer here, and actually for times which are good, okay, so for these types where you have typical behavior, you actually have at least one viscous layer. So there, let me draw it. So you actually have a zone of width nu, where you have a slope which is of order nu to the power -1. So that's the key idea for obtaining lower estimates for the structure, for these structure functions. Then you need to discuss about whether you are on the slope or you are outside it, but that's the key idea for the lower estimates. The upper estimates are a bit more pedestrian. Okay, there. I don't have very much to comment, but the main tool is a sharp use of Hölder's inequality and just a discussion of where you are in the picture here. But it's something which was conjectured by the physicists who understood the correct picture, but their proof was not rigorous at all. So now, I have enough time to touch all the topics which I mentioned. And first, let's make a small modification, and while remaining in 1D, let's consider a fractional dissipation. So lambda is the square root of minus Laplacian. You need to remember it's differential operator of order 1. And we put it here. So the case we considered before is alpha equals 2. As I said before, this is the setting where the fractional Laplacian is a very nice operator. You have no boundary. It's a usual Fourier multiplier, and which is, of course, non-local in the physical space. And the physical motivation behind it, at least the one I know of, it's study of combustion by two people here in Marseille, Clavin and Denet. And this is something which has been studied mathematically starting from 15 years ago. Boris, you can tell me if I missed some important reference on the subject, but it's, there was a paper by Alibois and Bervauvel, then later Alfaro-Drogneau. There was a very important paper to which I will come back by Kiselov, Nazarov, and Sterenberg in the very delicate case when alpha is equal to 1. And there was a nice, more recent paper in 2012 by Konstantin and Vikol. And there was also, okay, there's one paper which I really should cite, which is important, but it uses very different techniques, which I guess is why I forgot about it. It's Caffarelli and Alexis Vasseur here. So now this is maybe something I should have written before, which is an elementary scaling argument, which allows us to guess what's the interesting space scale. Okay, so characteristic length scale, it is not a very rigorous term, but here it's the typical width of the viscous layers. We can guess what it is actually by a simple heuristic argument. So as I said before, let's totally forget about time scales. So we just ignore this term, and let's derive in a consistent way, heuristically, what's the interesting value of L. So every time we make a derivative in space, we need to pay by dividing by L for dimensional reasons. Okay, so by the Oleinic estimate, we'll only consider the cases where the Oleinic estimate applies. So we have assumed that the solution itself, it's of order 1, and the two sides of the equal sign, we have to have an equality, which just gives you that this length scale L behaves as nu to the power beta, where beta is equal to 1 divided by alpha minus 1. So, okay, there is a case where obviously something is wrong. It's when alpha is between 0 and 1, because in this case beta is negative, and you have a characteristic length which is larger than 1, which makes no sense because we're on the circle, like no larger scales can exist. And it's normal that in this case nothing makes sense because, well, under a straightforward assumption that the initial data is large enough, the solution stops being smooth. And again, the crucial argument is to combine the calculation, so the dissipation and Oleinik's estimate. So in this case, when alpha is smaller than 2, this fractional Laplacian is an operator which has a negative kernel. So we still have Oleinik's estimate, which means that the squared L2 norm decays still again as t to the power minus 2, except that now we have this has much stronger implications than in the case with the usual Laplacian. Because what happens now is that, so when you differentiate, okay, assuming the solution is smooth, if you differentiate the energy, the viscous term which remains is this one. Oops. And when alpha is smaller than 2, you can bound it from above by the W11 norm. And since you have an the Oleinik's upper estimate on the positive part of the derivative, you know that this is also bounded from above by a constant. Okay, actually, just for consistency, it's a constant times t to the power minus 2, but we don't really care. So in other words, when nu goes to infinity, the dissipation goes to 0, which is in contradiction with the fact that we have energy dissipation at a rate which doesn't depend on the viscosity. So again, the only way out is that the term due to the nonlinearity does not vanish, so the solution can be smooth. So now let me say a few words about the most analytically involved case, which is alpha equals 1. Alpha equals 1 gives you beta equals infinity, which can mean more or less anything. And actually in this case we still have regularity, and if you read the paper with Kiselev, Nazarov, Sternberg, and you rescale in an appropriate way with respect of nu, you do have viscous layers which are exponentially small. Finally, let me tell you just a word about why we don't deal with the hyper-viscous case. So when alpha is strictly larger than 2, actually then, okay, it's not yes, lambda to the power alpha is an operator which does not have a positive kernel anymore. So we have no Olenik's estimate and no good inviscid upper estimates. Of course, the equation is very nicely parabolic, that's not the problem, but we do not have nice estimates which do not depend on nu. So in other words, the nicest case with respect to the generalization of our previous methods, it's when alpha is between 1 and 2. And I will not rewrite the estimates because they are word to word the same as in what I presented before. And the only difference is exactly the expected one. The parameter nu needs to be replaced by nu to the power beta, which is the new characteristics width of the viscous layers. And actually, well, the proof uses a very nice result, which is a quantitative lower bound. So again, you have to do a little bit like we did in the proof of Olenik's estimate. You consider a function, you see a point where it reaches its maximum, and now you have to have a bound on lambda to the power alpha u. So when alpha is 2, it's the minus Laplacian, it has to be positive, but you can't tell anything else about it. It's just by Taylor's formula, it has to be positive, and that's it. On the other hand, when alpha is smaller than 2, it's a non-local operator, so you can catch something much nicer, which is a quantitative lower bound on this term. And then we can play the same machinery as before, and we obtain optimal upper bounds on our solution. And then the lower ones, it's again, you have an energy dissipation argument, and Gallardo-Nirenberg allows you to propagate one lower estimate to get all of them. So in the remaining 15 minutes, let me tell you about what happens with if you add random forcing. And first, let me tell you what I mean by random forcing and what it means. How does it change the energetic nature of the system? Okay, so you have the same nonlinearity and the same dissipation as before. And you add the weak derivative in time of a Wiener process. So it's a Wiener process on a functional space, let's say L2. So it's a Wiener process in an infinite dimensional setting. The easiest way to do it is the following. And one important element, I said it's in L2, but we actually want it to be smooth in space. There is one standard way to do it, which is to define the Wiener process like that. So we still have the constraint that we want the space average to be 0, so there is no constant modes. You need to separate the modes which are relative to the cosine and the sine. And you put independent Wiener processes on each Fourier mode. And just one last remark: like that, it makes no sense. It's not in L2, so it's not a good. It's not a functional setting which we know how to deal with. So to make everything nice on the PDE level, we take alpha k and beta k, which go to 0 fast enough. Well, exponentially is more than enough. That's one thing which is more or less sharp with respect to our methods. Like super polynomially for any polynomial is more than enough in order to be able to differentiate in space. So here is what we do, and it has an important consequence on the system. So now, because of the Ito formula applied to the usual energy, the L2 norm squared, it is not anymore a purely dissipative system. We have two effects which compensate each other. Energy is dissipated through the Laplacian, but on the other hand, we have a constant rate of pumping of energy into the system, which is due to this to this noise, which is smooth in space and white in time, as a weak derivative in time of the Wiener process.
It's not conservative.
What is not? You mean the? No, it's not conservative, but it converges to a steady state. It has a unique stationary measure. I don't know if it answers the question.
But you started with some conservative law, but now you had something that destroyed it.
It was not conservation law to begin with anyhow, because we had the dissipation.
No, it's conservative of U.
Ah, the integral of U? Oh no, the integral of U is still conserved, because we have no we have no constant okay, we have no constant modes. We have modes yeah. No, it's, well, I'm sorry, but if I put on the light, it's even worse, because you can't really see you can see the slides very well. And now, okay, sorry. If you remember before, when we averaged Sobolev norms, we averaged in time, but now the brackets which we used before, we need to change the meaning. Okay. So one modification is kind of obvious. You need the expected value, because you now have a stochastic PDE. The other modification is a bit more subtle. So we still need to average over a time interval, because we use some estimate where we have the rate of dissipation and we need to average in time. So unfortunately, we have no choice. We still need to average in time. But now the starting time, when we start to average, you can take it as large as we want. Because now, unlike before, when we just dissipated and we couldn't wait for too long, now we just have energy which is pumped all the time into the system. So we can go as far as we want. Actually, Actually, for this equation, there is a unique stationary measure, and you converge to it with a rate which does not depend on the viscosity. So actually, you can average over intervals which are smaller and smaller in time if you allow t to grow larger, because you will reach the stationary measure of the system in the infinite time limit. No, I'm not very happy that this time averaging is here. It doesn't make much sense, but the methods really don't allow to remove it. I will not rewrite the results, because now they're really exactly the same as in the deterministic case. Well, except again, I said the meaning of the brackets change. So obviously we need Ito's formula, because this is how you adapt the energy method when you have an additive force. But you also need some more refined, stochastic tools, like the Burkholder-Davis-Gandhi inequality, to make things work. So now let us talk about the multi-D equation. So the multi-D generalization is pretty much the straightforward one you would make if you deal. So this is not a system because you are in the multidimensional setting, but U has the same number of components as the dimension. And you are still in the periodic case, so you're on the torus. Okay, here again, you can just think about it as the Navier-Stokes nonlinearity U nabla U. Okay, you again, you have a convexity constraint on F. So, but there is one assumption which we can't do about, because without this assumption we have no Olenik's estimate, which is that U is a gradient of some potential psi. Actually, it suffices to take the initial condition to be a gradient, to take, well, here as you see the forcing is already a gradient. So this is something which is conserved by the flaw, and an easy way to see it is just that you take the potential at the initial time 0, then you make psi solve the viscous Hamilton-Jacobi equation of this type, and then the gradient of psi will solve this multi-Debberger's equation. So what do we expect? We expect a tessellation of zones in the inviscid limit. We expect a tessellation of zones where the solution is smooth and which are separated by shocks. And the shocks are expected to be of codimension 1. And finally, so if we look in the directions on slices in directions which are transverse to the shocks, then we expect that the projection along this direction behaves like a 1D solution of Burgers. So this is what astrophysicists predicted. And actually, if you take this and you use a Fubini type argument, then you expect to so the estimates for small scale quantities and the estimates for Sobolev norms to be exactly the same as in 1D. So you expect the dimension to play no role. So before I tell more about the results, just a few words about how you need to modify the formulation in the multi-D setting. So there's nothing tricky. It is a straightforward thing. For the Sobolev norm, you just need to add over all possible multi-indices of length m for the Sobolev norm in WMP. For the increments, you need to remember one natural thing, which is that now the increments can be taken in many directions because you're not in 1D anymore. So you need to average over the sphere of radius L. And for the spectrum, nothing changes, except that n is, of course, a vector now, when you consider the Fourier modes. And again, I will not rewrite the results, because they're almost exactly the same. And here you don't even need to change the exponent to the viscosity coefficient. Okay, there is one very, very small difference, which is that p equals infinity is forbidden. And these are the results in the case where we have a stochastic forcing. In the deterministic case, we have something which is a bit annoying, which is that, as I said before, in the energy dissipation relation, the contribution of the nonlinearity will not vanish. When you have stochastic forcing, then you can be smart and make the solution go to the region where you want it to go, so that the contribution of the nonlinearity can be neglected. In the deterministic case, you can do whatever you want, so you need some kind of mild anisotropy assumptions on the initial data. And just one thing, there are really no obstacles to combining the multi-D and the fractional dissipation term, but it's just, I think it would be very long. I mean, the multidimensional paper is already around 50 pages long, so it's, I see no specific challenge, but it's not something I have looked at yet. And by the way, my fractional paper is in a purely deterministic setting, but again, I really see no obstacles to combining a fractional dissipation and this kind of random forcing. So now let me conclude. So we have exact and rigorous small-scale estimates. It's a broad class of models, where we have an inviscid upper estimate, so variations on the Olenik estimate. As I said, in the small-scale estimates, you have no dependency on nu. The only dependency on nu is the range of validity of the estimates, but actually the smaller nu, the larger the range where the estimates are valid. So you can make nu go to 0, the estimates are still there. And when you consider the stochastic forcing, then you can make t go to infinity. And when t goes to infinity, the expected value, then you go to the stationary measure, and you can get rid of averaging in time because you have ergodicity. And now it's something I wanted to tell about, but the paper is not yet on archive, but we really have the essential argument. It's a very promising work with Piotr Biller, Grzegorz Karch, and Philippe Laurenceau on aggregation-diffusion equations. And it's equations where you have a similar picture in terms of blow-up for nu equals 0 and nice parabolic estimates when nu is larger than 0. And there are no good inviscid upper estimates, but I think that why everything works there is that there is a very naive reason. So it's aggregation-diffusion type estimates which measure the concentration of some biological quantity. So of course the solution has to remain positive, and this is of course an obvious lower estimate. And actually there is a minus sign when you compare it to the Burgers type model. So actually it opens more perspective on models where you have something like that and you have the positivity assumptions, because of course from applications there are many models with positivity assumptions. So in the first years after my PhD thesis, I was a bit frustrated that this model seemed to be a bit specific. So I'm very happy about this, and it will be on archive soon. And it is also a setting where it will be very interesting to look at how you can introduce randomness. Well, except randomness will be more tricky. As I said, it's equations with positive solutions. So if you have positive solutions, additive forcing makes no sense. You need to consider multiplicative forcing, and it is more delicate. So before finishing my talk, here's a small bibliography. This is the paper which we are currently drafting. Okay. These are 3 of the papers on which the talk is based. There's also the paper with the fractional Laplacian. And here is a book which is, the goal of this book I'm currently finishing with Sergei Kuksin, is to put all the things about stochastic turbulence on a more rigorous probabilistic terms. And there's Sofiane Martel, who is here, who also finishes his PhD, where this kind of results are revisited from a more probabilistic perspective. So I would like to thank you again and to thank the organizers again.